Hello everyone, welcome all back. In this video, we are going to see steady state diffusion through stationary medium. The stationary medium is nothing but plane membrane. Now, consider a plane membrane of thickness L. I am considering a plane membrane like this, and the thickness of this membrane is known as capital L. Okay. The concentrations of the fluid at the opposite wall faces are Ca1 and Ca2 respectively. So here the concentration of the fluid on the left hand side is known as Ca1 and the right hand side is known as Ca2. Now consider this is a container, and in the container I am placing a plane membrane in the center of the container, and here one liquid is filled and here another liquid is filled. Here the plane membrane thickness is L and I am taking from this direction as X, right? So by using the Fick's law, we can find out the molar flux, that is MA, M dot A, molar flux in the sense M dot A divided by A is equal to minus DAB, that is the diffusion coefficient, into Ca2 minus Ca1 divided by L. This is the formula for plane membrane diffusion, right? The same formula can be rewritten as by bringing this minus here. So DAB divided by L into this minus and this minus become plus. So Ca1, this minus has to come here and this is minus Ca2, right? So both these formulas you can use. These formulas are available in the data book itself, right? So in the after page number 175 in the hidden mass transfer data book, for mass transfer for steady state diffusion through plane membrane, this formula will be given, right? So in this formula, this M dot A is known as molar flux, that is kilogram mole divided by S into 1 divided by meter squared, right? So the area is meter squared, which is equal to the diffusion coefficient is meter squared per seconds. This value will be given in the problem itself, or you can take from the data book, right? So L is known as meter squared, right? So this L value differs for the cylinders and spheres. For cylinders, L equal to R2 minus R1, where A equal to, you have to substitute here area value, no, A equal to 2 pi L into R2 minus R1 divided by ln of R2 divided by R1. This value you have to substitute for area value, right? So for sphere L equal to similarly R2 minus R1, where A equal to 4 pi R1 R2, right? These two formulas you have to know. This will not be available in the data book, right? While solving the problem, you have to use these formulas for area and thickness of the plane membrane, right? Now we are going to solve the problem. In the first problem, this is the first problem. In the first problem, it is given that gaseous hydrogen is stored in a rectangular container, right? The walls of the container area of steel having 25 mm thickness, right? So the thickness L equal to 25 millimeter, which is equal to 25 into 10 to the power minus 3 meters, right? So at the inner surface of the container, the molar concentration of the hydrogen is 1.2 kg mole per meter cube. So the molar concentration is Ca1 equal to, at the inner side I am taking Ca1 and the outer surface I am taking Ca2, right? So at the inner surface it is 1.2 kilogram mole per meter cube, right? This is given in the problem, while at the outer surface of the container the molar concentration is 0. So Ca2 equal to 0. Now calculate the molar diffusion flux, that is molar flux for hydrogen through steel, that is the plane membrane is steel. Take diffusion coefficient DAB is 0.24 into 10 to the power minus 12 meter squared per seconds. Here the diffusion coefficient is given in the problem itself, right? So now you have to find out the molar flux m dot A divided by A, right? So you know from HMT data book, write the page number. I think it is 173, right? 173. In that page number, the formula for molar flux in the plane membrane problem is given as dAb divided by L into Ca1 minus Ca2, right? Substitute dAb as 0.24 into 10 to the power minus 12 divided by length is 25 into 10 to the power minus 3 into Ca1 is 1.2 minus 0. You will get the answer as 1.15 into 10 to the power minus 11 kilogram mole per S into meter squared. Right? This is the answer. And in the next problem, hydrogen gases at 3 bar and 1 bar are separated by a plastic membrane. So here also plastic membrane, the word is given, so it is a membrane type problem having thickness of 0.25 millimeter, right? So first write L equal to 0.25 millimeter, which is equal to 0.25 into 10 to the power minus 3 meter, right? So the thickness is given, right? Second thing, hydrogen gases at 3 bar and 1 bar are separated. So on the left hand side it is 3 bar, on the right hand side it is 1 bar. So P1 equal to 3 bar, P2 equal to 1 bar. So you know how to convert the bar into Newton per meter square, right? Next thing, the binary diffusion coefficient. The diffusion coefficient value in plastic is given, right? So this is how you have to take the diffusion coefficient value in the data book. So here it is given that hydrogen and plastic, right? Hydrogen and plastic. For hydrogen through plastic, the diffusion coefficient is 9.1. So same thing will be given in the data book itself, right? So here in the problem itself they gave the diffusion coefficient dAb equal to 9.1 into 10 to the power minus 8 meter squared per seconds, right? Next thing, the solubility of the hydrogen in the membrane is 2.1. This value also available in the data book. If in case in the problem it is not given, you have to take the value from the data book only, right? Solubility equal to 2.1 into 10 to the power minus 3 kilogram mole per meter cube bar, right? And uniform temperature of 20 degrees Celsius is assumed. So T equal to 293 Kelvin. Calculate the following. First one, molar concentration on both sides. Then molar flux of H2 and mass flux of H2. Now we are going to solve the problem. Solution. First thing you have to find out Ca1 and Ca2, right? So just memorize this formula. Ca1 equal to solubility into pressure 1. That is solubility equal to Ca1 divided by pressure. From this formula I am writing this, right? So this formula just memorize. This will not be available in the data book. So once solubility is given, you have to find out Ca1 or pressure 1, right? So in the problem, solubility is 2.1 into 10 to the power minus 3 into pressure is 3 into 10 to the power. So here it is given in the bar. So I have to substitute here also in the bar itself. So that only this value into 3 bar, this bar and bar gets cancelled, right? So that is why I am substituting in the bar itself, right? So this value is 6.3 into 10 to the power minus 3. Similarly, Ca2 equal to solubility, that is 2.1 into 10 to the power minus 3 into pressure 2, that is which is equal to 1. So the final answer is 2.1 into 10 to the power minus 3. The unit for both things is kilogram mole per meter cube. Here also kilogram mole per meter cube. Okay. So now you have find out the molar concentration of H2 on both sides, right? So that is what in the asked in the first subdivision, molar concentration on both sides, that is Ca1 Ca2. In the second subdivision they are asked to find out molar flux of hydrogen. So molar flux is known as m dot A divided by A, right? So this value, you know the formula, DAB divided by L into Ca1 minus Ca2. Here you know the value of Ca1, Ca2, diffusion coefficient is given in the problem itself, length value also given in the problem itself. Substitute all the values, you can find out m dot A divided by A as 1.52 into 10 to the power minus 6 kilogram mole per second meter square. Then you have to find out mass flux. So here the mass flux is equal to molar flux into molecular weight m. Now molar flux is 1.52 into 10 to the power minus 6 and molecular weight of the hydrogen is 2, right? So here the answer is 3.04 into 10 to the power minus 6 kilogram per second meter square, right? So here I am substituting the number of molecules, no, so this mole gets cancelled and kg per second meter square will come, right? Now in the next problem it is given that oxygen at 25 degrees Celsius and pressure of 2 bar, right? So in the given data just write temperature T equal to 25 degrees Celsius, that is 298 Kelvin, right? So pressure of 2 bar, so P equal to 2 bar is flowing through a rubber pipe of inside diameter 25 mm, is flowing through a rubber pipe of inside diameter 25 mm. So D1 equal to 25 mm. It can be converted into 10 to the power minus 3 meters and the wall thickness is 2.5. So T equal to 2.5 millimeter, right? The diffusivity is 0.21. So that is the diffusivity measurement DAB. DAB equal to 0.21 into 10 to the power minus 9 meter squared per seconds and solubility is equal to 3.12 into 10 to the power minus 3 kilogram mole per meter cube bar, right? Find the loss of oxygen by diffusion per meter length of the tube, right? Here in the problem it is given that it is a tube. Once you see the tube in the problem, you don't consider that it is a equimolar diffusion problem. You just consider a tube. In that tube itself, the diffusion is happened to the atmosphere, right? So now through the wall of the tube the diffusion happens, right? In this case you have to take the plain membrane problem only, right? First thing, once the solubility of the component is given, you have to find the molar concentration. First one, molar concentration Ca1 is equal to solubility into inner pressure, right? So this value will be 3.12 into 10 to the power minus 3 into inner pressure is 2. So 6.24 into 10 to the power minus 3 kilogram mole per meter cube. You know why I am substituting Q as the pressure in terms of bar, you know that, right? So similarly Ca2 equal to solubility into outer pressure. Outer pressure is atmospheric pressure, that is 0. So Ca2 equal to 0, right? In the bracket just write assuming the partial pressure of O2 on outer side of the tube is 0. So here I am putting pressure as 0, so the value becomes 0, right? Next thing, you have to find out the molar flux, right? So the oxygen is diffused through the tube wall and escaped to the atmosphere. So now if you find out the molar flux per meter squared, then that will be the diffusion rate, right? So molar flux formula, you know that m dot A divided by capital A equal to DAB divided by L into CA1 minus CA2, right? So here the tube is in the form of cylinder. So for cylinder, L equal to R2 minus R1 and the area equal to 2 pi L into R2 minus R1 divided by ln R2 divided by R1, right? So now I am going to substitute all the values here. So m dot A divided by area is 2 pi L R2 minus R1 divided by ln R2 divided by R1, which is equal to DAB divided by R2 minus R1 into CA1 minus CA2. Okay, these R2 will get cancelled. So m dot A becomes 2 pi L DAB CA1 minus CA2 divided by ln R2 divided by R1. This is the final formula. Substitute all the values here. You will get MA as 4.51 into 10 to the power minus 11 kilogram per mole. Kg mole per seconds. Okay, this will be your final answer. That is diffusion rate through the wall of the rubber tube. Okay. Thank you all. In the next video, we will solve some problems on steady state equimolar counter diffusion.